So learning about the, oh yeah, okay, sorry, David. Okay, so this is Fourier week. So so the idea is to fight our way into the Fourier transform, which, as I mentioned at the very beginning, understanding this is useful for a lot of different things. It's not just MRI. It has a lot of applications to all different fields, to processing images, visual images, processing sounds, processing time series data. So it's worthwhile. It's a worthwhile thing to learn, even if you didn't care about MRI. So the plan is just basically go over the Fourier transform equation and then illustrate it for a simple special case, which is I think the easiest to understand, and that's the special case of the Fourier transform of a real valued signal. So the Fourier transform transforms complex numbers into other complex numbers, but you can always think of a real number as a complex number that just has a zero imaginary component. So and that turns out to be the easiest case to deal with. And so I have in the notes, I have a page on complex arithmetic, complex algebra, and so basically it has to do with looking at something like, e to the minus I some angle. And the way we think of that is we think of that as a vector on the unit circle of length 1, and we can sort of decompose that vector into a real and an imaginary part. And if you look at this, what is the real part? The real part, just since the hypotenuse is 1, the real part is just cosine of that angle, and the imaginary part just equals sine of that angle. So you immediately see the relationship between this thing and sines and cosines. And you might wonder, like, what does minus mean? So another way of writing this, you could just write it as e to the I minus phi, like that. That's the same. And so what does minus mean? Minus just means, an angle like that. So that would be, minus phi. Sorry, I got a little bit too many things in there. Yeah, so the minus just sort of makes the angle, just flips the angle around the x-axis, around the real axis. So this guy is minus phi. So when you look at, just to quickly review what we went over on complex numbers, so to add them, it's just a vector sum. So you just think of these numbers as two-dimensional vectors, and you add them by just tip to tail, and multiply. The simplest way of thinking of it was geometrically was multiply amp. So multiply amp and then add angles. So we're going to actually look at the equations that I'm going to write out are the ones for the components, and the ones for the way you multiply complex numbers with components is more complicated. Remember, I wrote it out as a little matrix times a vector, and so there was more things. But this is the geometrically easiest way to think about the multiplication. And the reason why we mention this is that the Fourier transform involves both addition and multiplication of complex numbers. So we need both addition and multiplication. So that was our quick and dirty intro to complex arithmetic. One other thing about complex arithmetic that's worth mentioning is that complex arithmetic, complex multiplication commutes. So you can put, it doesn't matter what order you put the two complex numbers that you're multiplying. They can go in either order and you get the same result. So that's different than the cross product. The cross product, it matters what order. If you flip the order, you get the negative. You get a similar vector, but it's the negative of the vector. And so complex multiplication does commute, so you can do it in either order. Okay, so let's start off with the Fourier transform equation. And so the Fourier transform equation, I'll write it, the Fourier transform as a capital letter, and then the non-Fourier transform as a lowercase letter. And I'm going to just start off with, to me, the most intuitive starting point, which is the Fourier transform of a signal in time. So you have a whole series of time points, and you want to do a Fourier transform and turn that into a series of frequencies. So when we get to MRI, we're going to be talking about spatial frequencies. So the Fourier transform is applied to spatial frequencies in MRI. But we'll start with the temporal frequencies because, like I said, that just has at least for many people, that's kind of a more intuitive starting point. So this says the Fourier transform as a function of frequency. So that means that we're going to get a whole bunch of different frequencies here. And then the Fourier transform equation is to first take the sum across all time. So this is, you can write out a discrete Fourier transform where you just have a fixed number of points, and of course that's what we're going to be doing when we talk about MRI. We don't collect an infinite number of data points. But we'll just start off with this sort of integral version of it instead of our sort of sum version of it. But basically it's a sum across all time of the following thing. And so the following thing is the non-Fourier transform function, which is a function of time, not frequency. And then that's multiplied by this e to the minus t minus I 2 pi f t. Okay, so now when you first look at that, if you're like me, you're going like, wow, there's like 1, 2, 3, 4, 5, 6, 7 things there. So we have to explain the 7 things there. And then last but not least, we are integrating. This is the little fragment of time that we're calculating for each element in the sum. So that's the Fourier. So there's not too much to it, really. It's when you look at it, it's basically, you can basically think of it as a dot product, because you've got a whole bunch of these things, a whole bunch of time points, and then you have a whole bunch of these things. We'll explain what those are in a second. And you just basically multiply them all times each other, and then you sum them up. That's basically a dot product. It's an infinite dot product, sort of over infinite amount of time, but it's basically a dot product. So it's kind of, it's really the correlation. This is the correlation between this signal and whatever this is. And that's the way we're going to sort of break into it. It's just think of it, the Fourier transform, as 2 correlations. 2 or 4 correlations. We'll start off with 2. Now, when you look at an equation like this, the critical thing is to sort of see, so you can see you've got time here, and then time is over here. and then time is up there, and then time is over there. So that's the thing we're summing over, the index that we're summing over. And then if you look at frequency is here. So this is this is for one frequency. So for one, that's how we calculate this sum for one frequency. And so we would have to change frequencies and then recalculate the whole mess to get another frequency. So what we're going to go over is just one frequency to show how to calculate this Fourier transform complex number for one frequency. Now, what are the actual things we're talking about here? So this thing right here. So this thing is a complex number. So that means it's got a real and imaginary part. But frequency is real. So frequency, so that guy is real. It's not a complex number. So time is not a complex number. And then here we've got another complex thing. So I said we can always think of a real signal, say like a time signal, like an audio signal. We can always think of that as a complex number if you just assume that the imaginary part is 0. So what does that mean geometrically? It just means that the imaginary part here, the imaginary axis is 0. So that means that you'd have a vector, and the vector could go negative or positive. So the way you would plot out a signal like this, sometimes it would be a big vector, and then sometimes it would be a negative vector, and it would stick along. It would just stick along the real axis and not go up into the imaginary axis at all. So that's what a time signal would be. It's a complex valued signal, but the imaginary part always has to be 0. So you have to have a complex input to the Fourier transform. So and then again, this thing right here is a real number. So time is a real number. So that's just one number, whereas the complex h at time point t has to have 2 numbers. So then we get to this mess. Okay, so what is that mess? So that mess is, it's basically a vector, so it's complex. Complex vector amp equals 1. So it's a complex vector of amp equals 1, pointing in direction of this thing, which is an angle. So that whole mess is an angle. So we're using cycles per second instead of radians per second. If you used radians per second, you would just have omega for this 2 pi f thing. So you just have one number instead of 3. But that thing's an angle. And how is that an angle? That's an angle because you've basically got cycles. So 2 pi is just a number. It doesn't have any units. F is cycles per second. How many cycles per second? And then you multiply that by seconds, and you get cycles. And what is cycles? Well, cycles is like 2.1 cycles is an angle. It's an angle like 370 degrees. 730 degrees. So 2.1 cycles, equals 730 degrees. So that's an angle. So pointing in direction of that angle. And so the angle is 2 pi f t, all 4 of those things. So that's our Fourier transform. So what does that mean? This thing is real again. That's another real. That's a little real fragment of time. It doesn't have. So it's important to sort of keep all these things in mind. And then last but not least, this is complex multiply. CPX mult. So that's one of these things down here, multiply amplitude, add angles. This guy is real. So it's complex multiply, and then this thing here is complex add. So this whole operation says for one frequency, what we do is we take a whole bunch of different time points, and for each one we multiply it by this thing, which is going to be this vector pointing in some direction, which will change because for each time point we're going to insert a different t here. Yeah, so for each time point you'll insert a different t, and so the angle of this thing is going to change for each different time point, and you complex multiply them doing this multiply amplitude add angles, and then you add up the whole mess, and what is that? That's vector sum, so you sum up all those vectors, and then you get one complex number for a particular frequency. So that was the long, wordy explanation of this equation. So there's really not so bad, but it takes a little while to sort of work through all the parts. And one of the things with, if you're like me and you don't know much about math, when you come up to something like this, you just typically go you make 2 saccades or 3 saccades, and you go like, it's some kind of math, and I'm not really paying that much attention to it. That's okay. When you actually know math, that's a good way of looking at it. But when you don't know math, the way you have to look at it is I look at h and then parentheses and then f and then equals, and then I look at the integral sign and I say, what is the integral sign over? And then I look at h and then parentheses t, and then I see maybe they leave this out, but if they left it out, I say, why did they leave it out? Then I look at e, and then I have to look at each one of these things separately, just to make sure that you see every one. So that's why I always annotate every one, so to make sure that you look at every one. So now the plan is, what does it mean concretely with a real signal? And so the first thing we can do is to write out in detail what multiplications of real numbers you need to do one of these terms in the sum. So what is the Fourier integral term? So Fourier integral, so that's the Fourier integral single term. So what multiplications do you have to do of real numbers, not complex numbers, real numbers, to calculate this complex multiply? And so if you write them out, once you know how this works, you don't even bother with that. You just kind of let MATLAB do it. But I think it's important at the beginning to just get some idea of like what's actually going on. So there's the Fourier integral term is a complex number, so it's got a real and an imaginary part, and so I'll write out the real and the imaginary part. And so it's starting off with the real part of this signal at a point in time, particular point in time, and then we multiply by the cosine of 2 pi f t, that whole mess, and then plus the imaginary part of the signal at a point in time, which you notice in the case of a real signal would be 0, times the sine of 2 pi frequency t. And frequency is whatever the current frequency that you're working on, and time is also whatever the current time point you're working on. So those will be substituted with whatever the current values are. So that's the real part. And then the imaginary part is minus the real part times the sine of 2 pi ft plus the imaginary part times the cosine 2 pi ft. Okay, so that's the whole mess written out. So it's actually 4 correlations. You sort of correlate the real signal with the cosine, correlate the imaginary signal with the sine. All told, that whole thing equals the real part of our output number, and then correlate the negative of the real part with the sine and the imaginary part with the cosine, and that equals the imaginary part of our 2-component complex number here. So if you notice that if we have an imaginary part that happens to be, if the imaginary part happens to be 0, like we would have in the case of a real signal that was just stuck on along the x-axis, along the the real axis, then these two will dump out, and we'll just end up with this. And so the full Fourier transform with a complex signal that has an actual imaginary parts to it is going to be 4 correlations. We're adding 2, we calculate 4 correlations and add the first 2 together to get the real, and then the second 2 together to get imaginary. But in the very simple case of a real valued signal, we just have 2 correlations. So that's the bottom line, and so that's the way we're going to draw it out. Like, what do those 2 correlations mean? So this is 2 correlations for real valued signal. So I found that was, for me, was the easiest way to fight my way into the Fourier transform. So let's just take an example of a real. I'll leave out the negative for now, but we can insert that later. The most important point is to see why it's a correlation. So let's take our real signal. So here's our real signal, and make sure I got enough room there. Complex add. Okay, so we've got our real signal, and we'll just think of this as a time signal. So here's a signal over time. So here's our real signal, and here's our imaginary signal. So the imaginary signal is 0, and the real signal is just some time signal. So here's some time signal. Okay, so what does the Fourier transform says? It says basically just correlate that with a cosine and a sine. But there's all those things in the argument of the cosine, so we have to take account of that. So basically, so now we have our e to the minus I of some angle. So what is, actually it's right out the thing, e to the minus I of 2 pi ft. So what is that whole mess? So now we have to draw that out as a function of time. So this is time in this direction. So we're still in time. So what are we doing? We're trying to do basically a complex multiply. of this thing times this, these two things. So what are these two things down here? Well, if we use the example I have in the notes is frequency equals 3. So I'll put that here. For example, frequency equals 3. So this is, you know, e to the minus I 2 pi ft. But we're sticking in 3 for here, for frequency. And because we can sort of view it as a sine and a cosine, then basically we just have, here's the cosine, and here's the sine of that complex number. And if it's a cosine, if we've got f inside the cosine, so if we've got sort of, you know, f inside the argument of the cosine, that's going to make 3 bumps. So, so let's draw like a 1, 2, 3, almost. Okay. So that's our cosine of 3 bumps. And then what's a sine of 3 bumps? So sine is like a much better sine than cosine. Okay, so that's our sine of 2 pi f 2 pi 3t. And this is cosine of 2 pi 3t. So this is still time here. So this is still time going this way. So time is what's causing the bumps to go up and down because you keep incrementing time. And then 3 determines how many bumps you got. So if it was 1 in there, you just end up with a single sine. If it was 20, you'd end up with 20 bumps. So this is a graphical representation of what this function here does, broken from a complex number into a sine and a cosine. And so now we have to do our complex multiply. So this is basically a complex multiply over here. And our complex multiply is in a special case where we've got the imaginary part, you know, for example, 0. If that's, for example, 0, then we just end up with multiplying it by a cosine and then a sine. So what does that look like? So it looks like, let's take a number here. So that's an h, the real component of t, and we multiply it by first the cosine. So we go down to here, we get whatever number that is, and multiply it by it. And then we go to another point and multiply the corresponding point on the cosine and another point, etc., across all the points. And then what do? So now we've suddenly transitioned into Fourier land. And so we're summing across all time to get one frequency. And so this all gets summed into just a single point down here. So that means, so now we're in frequency land, and we've got you know, real freak and imaginary freak. So it's important to remember we got 2 things down here. There's not just what the frequency is a real number, but the Fourier transform at a particular frequency is a complex number. And so we have a real component of the frequency and an imaginary component of the frequency. Or you could think of it as, you know, an amplitude of the frequency and a particular phase angle of the frequency. That's alternative way of thinking about it. We'll draw over to the right. So what do? So we take these things, and they all, since we're at frequency 3, here's 3, they all go here. So let's just say that was the number. So this guy gets summed, and this guy gets summed, and this guy, and this guy, they all get summed to that number. So we just get a single, when we correlate with the cosine, we get a single number, which is the real component of the Fourier transform at that frequency. Single number. It's a single number, it's not a complex number, just one number. So then we have to do the same thing with a sine. So we have to do the same thing with a sine for the imaginary component. So here's the imaginary component, and I'll draw that one in blue so we can see it a little different. So now what's that going to be? So that's going to be take this same data point here, but instead of going down to the cosine, go to the sine. So here's that same data point, and then we'll go over and get the sine. Same data point, get the sine. And again, last one. And do that for everybody. And then sum all those guys up. So then after you multiply them, and again, the way I'm writing it out here, you don't have to sort of worry about complex multiplication. These are just real numbers. These are all just real numbers that you're multiplying by each other. So we add that guy up here, and this guy goes, so add them all up. And then we get the real component. And then just do the same thing for every number of bumps. So start with just one bump, two bumps, or since this is an integral, we start with one bump and then 1.001 bumps and then 1.002 bumps, etc., all the way up to like 1,000,000 bumps. Okay, so now we've entered Fourier land. So here's the divide right here. So we're now in frequency land. That's the big divide. So if we did that for everything, what would we end up with? We would end up with the real frequency spectrum and the imaginary frequency spectrum. So what are these going to look like? Well, they're going to be, now we're in frequency land, so everything is as a function of frequency rather than time. It's a function of frequency across the entire. So there'll be some. So this is frequency in this direction. So there'll be some set of numbers, and some other set of numbers here, like that. Now we typically don't look at it this way in sort of real and imaginary. What do? We typically convert. We convert to polar coordinates. And so, how would we do that? So we've basically got some vector that has a real and imaginary part. And to convert, so what is the amplitude? The amplitude, amplitude equals the square root of real squared plus imaginary squared. So that's how we get the amplitude. And then what about the angle? This angle here is going to be, sure I'm not going off, okay. So that angle is going to be the arctangent of the real, it's usually listed as arctan 2 of the real and imaginary, or sometimes they do the opposite order. So what does that mean? It means the angle whose tangent, the angle whose tangent is, you know, real and imaginary. So you know, the tangent is a division. Okay, so that's how you would, like in MATLAB, that's how you would. There's other ways in MATLAB, other functions. You can just say, you can say real, or you can ask for the phase, or just ask for the amplitude in MATLAB. And then when we look at the Fourier homework later on, I'll give examples of all the functions you need for this. So if we do that operation, so convert into a length of the vector and angle of the vector, there's nothing to it really. It's just changing into polar coordinates, but that's typically the way that you always look at it. Then you have something new, which is the thing that you typically look at when you think of the Fourier transform, which is the amplitude spectrum. And then the phase spectrum. Now, you're probably less familiar with the phase spectrum because that's often thrown out. But, so what is that? So the amplitude spectrum is now going to be just how much of each frequency you have. So this is, you know, this is do that conversion from real and imaginary to angle and amplitude. So do that. This is typically when you say like here's a Fourier transform of an audio signal, you typically are looking at the amplitude spectrum. So this is going to be still frequencies. We haven't changed the y-axis, but you know, say you got a lot of this frequency in there and some of this frequency. So say that's frequency 9. So you got a lot of frequency 9, and maybe you got a lot of frequency 16, and then maybe there's some high frequencies in there. So that tells you the length of the vector, how much there is, but then you've got a second number, critical second number, which is the phase. And the phase, it could say, it will vary between, say, you know, pi and minus pi. So that's, you know, like between 180 and minus 180. And so there'll be, for each one of these numbers, there'll be a phase also. And that phase angle will be an angle that tells you what angle that amplitude was at. So basically the bottom line is if you've got a real signal, it's basically the Fourier transform. So ft, it's exactly equivalent to, so for real sig, ft equivalent to simply just correlating with sine and cos and sine. Cos and sine at each frequency. Now, so it's a very concrete thing. You're just saying how much does the signal look like frequency 3? How much does this look like frequency 4? But then you're finding another thing, which is what is the best fit? So the remarkable thing about the Fourier transform, because we're essentially decomposing this signal like a time signal, we're decomposing the signal into orthogonal components, means components that are at right angles. So sine and cosine are at right angles to each other. You can see they're at right angles to each other here. What does it mean to be at right angles? It means you're completely uncorrelated. And we'll talk about this next time. So a sine is completely uncorrelated with a cosine at a particular frequency. So if you take cosine, you know, so what does that mean? If we take cosine of 3 and sine of 3 and multiply them all by each other, multiply, you know, cosine times sine, add the whole mess up, we get 0. So a sine and a cosine are completely uncorrelated with each other. So that means if we calculate the correlation with a sine, with a cosine, the correlation with the sine is completely independent. You can't predict anything about the correlation with the sine from doing the cosine calculation. So what does that get us? Well, what does the angle mean? What does the phase, this phase spectrum angle mean? The angle means basically what is the best offset of a sinusoid? What is the best fitting offset? Because if it looks a lot like a cosine, it's not going to look very much like a sine, because a sine is orthogonal to that. And if it looks kind of halfway between a cosine and a sine, well, then it's going to be like, it's just going to be a shift halfway between a cosine and a sine. So how would you, so another way to calculate the Fourier transform, which would take like forever, would be to take a signal like this, like a sinusoid, like take a cosine, run the calculation with the real signal, get a number, that's a correlation or a dot product, and then move this guy over a tiny bit. So what if we just move this guy just a little bit over like that? And then did another correlation, get that number, move it over, keep moving it over a tiny bit at a time until you found the one that has the biggest correlation. That's exactly what the Fourier transform does, but it does it with just two correlations. You only need two. You just need a sine and a cosine, and then you're done. So just by calculating the correlation with a sine and a cosine, you will automatically come up with the angle that represents whatever the shift, this phase shift, that gives you the best correlation with your signal, your arbitrary signal up here. So, yeah, so that's the sort of remarkable part of the Fourier transform. And then the most mind-blowing part is that if you just do it again, you get back to where you were. That part's like, how could that happen? So if I take the Fourier transform of this thing and I get all these frequencies, and then if I take the Fourier transform of all these frequencies, I get my time signal back. So that's kind of, that just doesn't quite make sense. So you just do exactly the same operation again on your output, and it cycles back to time again. So this is very relevant. We have to understand this in order to understand how the image is made. So this is fundamentally how the MRI image is made. So what do you see, when you look at somebody's brain on the console? So here's somebody's brain on the console. What are you looking at? You're actually looking at the amplitude image. So the phase image was calculated, has to be calculated. So basically, you take your data off the scanner. So so in the middle. So what is MRI? So MRI is fiddle with gradients and RF to get signal that is FT of brain. That's one. And then two, do the inverse Fourier transform of it and get a brain. So that's pretty much all there is. All there is to the spatial part of MRI. It's a little more complicated when you look at the details, but basically that's what we do. So we fiddle with all the gradients and just end up with something that's actually a Fourier transform of the brain, and then we un-Fourier transform it and get the brain out. And then what do we do? Well, that gives us a real and imaginary part. The first thing we do is we turn it into an amplitude and a phase angle, and then we throw out the phase angle. It's useful for other things sometimes, where we throw out the phase angle and we just plot the amplitude. So that's what you see on the MRI console. You see just the amplitude image. The phase image is actually there, but it's been thrown out. It's used sometimes, for instance, for a field map. So when you do a field map, you actually look at the phase image. You look at two phase images and compare them to each other. So it's not like the phase is totally useless, but what you're actually looking at on the console is the amplitude image. It's just the length of the output of the Fourier transform. But it's critical, you know, you can't get the length on it unless you've got the real. You need the real and imaginary in order to calculate this length here. This is the, so here's the amplitude, and there's the phase spectrum. Okay, so I think I did a neater than average job of the Fourier transform. So David will end the recording now, and we'll ask for some questions.